In 2008, Bennett Foddy created this game called QWOP, and in fact, you might have heard of it. In 2010, when it hit my office, I don't think any work got done that day because everyone stopped and had to try out this game. It became an internet sensation for a little bit of time. The game is really simple. All you have to do is get the runner across the finish line at 100 meters. And the controls are deceptively simple. It's just QWOP. However, you're controlling more or less the individual muscles, or at least the big muscles, in the runner's legs. This makes for an extremely difficult, if not hilarious, control scheme as you're trying to get the runner to move forward. And because of the ragdoll physics, it often results in some hilarious crashes. With some practice, you can either scoot along or maybe start to get a stride going where you're, sort of doing this run marching thing. Because this game is so difficult for humans to learn how to play, I want to see if I can create an AI that learns how to play it on its own. To start, I asked some of my friends to see how far they could get in the game.
Games. Use the QWOP keys to move your legs. OP, QWOP. Ideally, you will run 100 meters, but our training program was underfunded. Remember, it's not about whether you win or lose. Okay. What? Oh, what? Wow, 2 meters is as good as I'm going to do. That's definitely better than my former time playing this game. Backwards. What about if you go backwards 2 meters? Okay. Okay, that's enough for me.
All right, let's see. Calves. Nope. No. What type of controls are these? You know what? I got 2 meters. 2.1.
2 meters.
As far as I'm going.
2 meters. Hey, wait! Look at this. I'm doing a knee at a time.
Were you practicing while I was playing?
No, the other way. Let my leg go over my head.
All right, here we go.
Oh,
Oh no!
4.7.
Well done.
She's doing it backwards though. She's doing it
Like the
just
moonwalk.
backwards.
if it was a limbo contest, you would have won.
Oh, recovered the
I think you
first
broke
time.
the record for going backwards.
Well, at least just fall over. Don't make me go through all this.
Bold strategy, Cotton. Let's see if it pays off.
There you go.
Oh, pick it up.
You went airborne.
Yeah.
Look at his concentration on the screen. Just look at it.
Go, John, go. Go, John, go.
Yeah, keep going.
Oh, 10 meters.
Come on, Nate.
Oh, no.
Once you panic, it's game over.
In my quest to learn more about AI, I want to try tackling this simple but frustratingly difficult game using reinforcement learning. Before we start, let's talk about what that actually means. Reinforcement learning involves training an artificial intelligence to learn from experience over time. It is broken into a number of different components with definitions that you should be aware of. First of all, we have the environment. In this case, QWOP is our environment. It's just the game, the screen we see, and the keys we can press to interact with the game. We usually have some sort of interpreter. This takes that environment in and assigns it an observation and some rewards that can be sent to our agent. In this case, the observation is the screen. Now, we might do some color correction, or we might lower the resolution so that our AI can learn a little bit more quickly. It also figures out some rewards, or rather we assign certain rewards, such as making it past a certain point or performing some sort of action, say keeping the head above some sort of threshold. We assign those rewards, and both rewards and observation go to the agent. The agent is in charge of taking in these rewards and observations and making a decision. This is where the actual machine learning takes place. Often this is something like a neural network where you have the observations come in and it produces some sort of action as a result of that neural network. And we use reinforcement learning to train that neural network or other machine learning model in order to produce those actions based on what it's seeing. The rewards are used during the model training in order to help the model figure out what actions it needs to perform. The actions then interact with the environment to change the state somehow. We're going to be using a wrapper known as Gymnasium. This acts as our interpreter and our, I suppose for lack of a better term, virtual arm to control the environment. Each time a step is performed in the game, the interpreter inside of Gymnasium will assign some rewards as well as take the observation and create something that the agent can use and learn from. Once the agent makes a decision, it will send that back to our Gymnasium wrapper, where our wrapper will then perform the actions. In this case, we're just going to be using another Python package to control the keys, the QWOP, and whatever's needed for resetting the game. To train the agent, we'll be using a framework called Stable Baselines. This is a collection of very popular and cutting-edge reinforcement learning algorithms. The specific algorithm we'll be using is Proximal Policy Optimization, or PPO. This was developed by OpenAI in 2017 and is considered one of the leading algorithms for learning a variety of reinforcement learning tasks. To create an AI to play QWOP, I'm going to do everything inside of a Jupyter notebook here, and rather than try to simulate it, say on a server, I'm just going to have it directly interact with a browser that I've put here. So if you're trying this yourself, and yes, I will be placing all of this code in a repository that I will link to so you can try it on your own. Note that I'm going to put the QWOP window in my upper left corner, just barely, and then I'm going to adjust the size of this window so that the scroll bars just disappear. And I'm trying to figure out where that is. So there's the left to right scroll bar. There's the up and down one. Okay. So I'm going to run through this notebook, and I won't go through each cell because I figured you can go through that on your own, and I don't want to take up a whole bunch of time, but you're going to need to install PyTorch, and I highly recommend doing this with a graphics card. Otherwise, training will take forever because we're doing this locally on the computer here. So I've installed PyTorch. You're also going to need Tesseract. You have to install that separately, and then you can install this PyTesseract, which is a wrapper. I've already installed these, so feel free to uncomment them and install them if needed. Here's my configuration, where I'm going to first import a bunch of libraries. And then the idea is I'm going to try to crop the screen just around the runner in QWOP, and then downsize that to 36 by 36 grayscale. Hopefully that's enough, because the smaller the image, the faster this thing trains and the better it runs, the more frames per second that I get, but I lose some information in the process. I'm also going to crop around the score, which is going to be this 0.3 meters. That'll be, I guess, my reward initially. We'll probably have to do some reward shaping later on. And then I want to look for this screen to figure out if done. So these are all my settings here. Oh, and for my actions, I'm going to do no op, which means do nothing. Don't press any keys. Press Q, press W, press O, and press P. And so now that we have that, let's create MSS, which is our screen capture object. We're going to try doing a screen capture here. You can notice down in this corner, that's what the game will be seeing. And I've also shown it right here. Let's try starting the game here. So I'll click to begin. I think I just broke QWOP. I think I'm winning. What is going on? Oh my goodness, I have discovered some fantastic new flip method in QWOP. Oh, this is amazing. And that's it. I beat QWOP. I'm done. I don't have to do anything else. Okay, but for real, let's try refreshing this page. What just happened? Okay, there we go. There we go. That's the QWOP we all know and love. So let's try capturing that window again. And you can see I've created a window down at the bottom left. That's going to be what the game sees, and that'll just be recurring as the training process happens. And this is the window. So we've downsized it to 36 by 36. We convert it to grayscale. Hopefully there's enough information here for the AI to learn kind of the position of this runner. We're going to use OCR, so that character recognition, to figure out what this is. So this is going to be part of the reward, is how far this runner goes, and that's given to us up here. So that's 0.2 meters, so that score is going to be 0.2. I think I'm a little too far to the right here, so let's move the window just so those bars disappear. And we'll try this again. Sure enough, there's nothing on either side. 0.1, that's reading correctly. Make sure my screen grab's still good. There it is. There's my runner. And then OCR to get the done screen. So right now it's looking at his legs. This is just looking for a particular string here. So let me purposely end this. And then I'm going to run this again. And sure enough, it's looking for this press space to restart. And when it sees that, it returns true. So we just have to turn these into functions and wrap that gymnasium environment around it. So then we can interact with our training algorithm, which is PPO, and that's part of stable baselines. So the next thing we want to do is test observation spaces. So this is just going to create our observation space, which should be that 36 by 36, and it's just going to assign random values in here. That's fine for now. And actually, this is not correct because it's not actually looking for 0 to 1. Stable baselines normalizes this for us. This should be between 0 and 255. So let's change that. There we go. That's looking better. And then I believe this should be integer. There's the conversion. We don't care about that. What we care about is this game information. So what do we have down here when we're actually creating this? Oh, this is being passed in. So this D type, this array D type. Okay, it is this. So we're just going to use this variable, and that's going to determine the values, the type of values inside the image array. So that 36 by 36, those should actually all be integers, not floating point. So there we go. That looks like a pretty good observation space. And this is just getting an example row from that. The next thing we want to do is test our action space. These are the actions that the agent can take. So in this case, we're just going to draw randomly from that, was it 0 through 4, so 5 possible actions. If I run this a bunch of times, you can see it was no op, then O, and then I accidentally clicked this box. But to show that again, there we go, no op, come on, give me something new. Give me something other than an O and a no op. Random is random. There we go. All right, that's the cue that can possibly be pressed. So now we're going to combine those together, and this is a test control interaction of the game itself. When I run this cell, you'll see that the mouse is going to move over here, and it's going to actually interact with the game physically on my computer, or I don't know, virtually, I suppose. I'm not trying to like create a server somewhere and use Selenium or one of those other wrappers. I'm just trying to mimic actual keyboard and mouse pushes, and it's just doing a screen capture. So let's try this. It's going to move the mouse over there, restart the game, and you notice the Q, W, O, and P get randomly pressed throughout that process. You can see that happening again here, and random things happen, and eventually it just kind of times out after 10 of those. Because it's random, who knows what our runner is going to do. The next thing we're going to do is wrap all of that into our gymnasium environment. We're going to start off by initializing this object where it sets a bunch of these variables. Each step, which is about once every 300 milliseconds or so, we get about 3 frames per second with this. So each step, it's going to be passed an action. That's going to actually take that action. In this case, I'm going to press the action, wait for a moment. In this case, it's like 50 milliseconds, and then release it. And then if it's a no-op, none of those keys get pressed. It's going to get an observation where it does that screen capture, and then it's going to look to see if the game has ended or if we've reached that timeout, because I'm only saying, I think it's like 5 or 10 minutes before we say, okay, you know what, just start over again. And then it's going to pass all of those out, or it's going to return all of that information. And then the training algorithm is going to take that information and do its training stuff, its training magic. Rendering is going to draw our little box down here. It's using OpenCV to make that happen so we can see what the game sees. Then we're going to, on the resets, this is when the game timed out or we reach that end position where the game needs to reset. In this case, it's going to press R, which is that reset position. It's going to move the mouse over here first, press R, and then reset all of my scores and get an initial observation, which it then returns to the learning algorithm. Close is called whenever the game is shut down. This should destroy all those OpenCV windows. The observation is where we grab the screen. It's this area in the screen. It's going to convert that to a NumPy array, change it to grayscale. It's going to resize it to that 36 by 36. We're going to reshape it so that one frame is on top. That's how stable baselines looks for these. It needs to have number of channels, and you can do a number of things with this. You could have RGB channels, you could have frame stacking where you stack, 5, 10, 15 frames if you want the algorithm to learn motion over time, and we may actually need to do that eventually. Getting the score is that OCR that we looked at earlier where it just kind of does a screen capture in this area, and it's going to extract the number of meters ran, so it's just going to convert that to a floating point number, and that's going to return it as a score. Get done constantly looks at this area of the screen for that, I think it was press space, whatever it was, that press space to restart. It's going to look for that and determine if the game is done. It returns true if the game is done, false otherwise. So that's our built gymnasium wrapper. And then we're going to create our environment because it's always a good idea to test your environment before running the learning algorithm. We're going to test our wrapper methods here. So sure enough, we get the score, 0.1. It's not done. Here is our observation. It's that 36 by 36 with one channel, and this is what the agent's going to see. So next, I want to test that game loop where it's everything together, but we're now controlling it with that environment. So here we go. We can see it randomly pushing some of these buttons. Hopefully it fails pretty quickly here. And it's over. And you notice I have 4 EP in range 3. That means do this 3 times. So we should see this one more time here. Come on. You got this. You got this. Sometimes it gets caught in a weird position. And then luckily I have a timeout here. I think it's like 60 seconds. Oh, 5 seconds. It doesn't last very long. So I just pass in the 5 seconds as a timeout. If the runner doesn't fall pretty quickly, it just resets the whole game. It just pushes R. This is a test I wrote for myself to determine that I can still do all of that while the lid is closed. I'm going to skip this test for now. And this environment checker, which I believe is part of stable baselines. It's not part of gymnasium. Because those two interfaces change constantly, it's usually a good idea to stick to a particular version of each of them. And then this is a way to make sure that the gymnasium environment that you created is going to work with stable baselines 3. So this is always a good thing to try, especially when you create your own environment. So it's going to do a couple of things here, make sure it can interact with your environment. And our guy's going to crash here. It might do a restart, and it's done. Okay, so the environment is checked. The next thing we want to do is create some custom functions here. So the checkpoint callbacks allow me to store the model as it's being trained. So for example, every 10,000 steps or 20,000 steps, it's going to save that model. So if something crashes and I need to come back to it, I can load that checkpoint model and continue to train from there. This is really handy because we're planning to train for 9, 10, 11, 12 hours at a time. And if something happens, I can always go back to a previous checkpoint and at most lose maybe an hour here, depending on what this checkpoint frequency is set at. I think it's set up to like 20,000, which is like an hour and a half. That's fine. So we're going to set that checkpoint and we're going to pass that into our training algorithm so it knows to call this. I believe it actually calls it every step, but then we have a check here to say if ncalls is divisible by check frequency, go ahead and save the model. All right, so we're done with that. The next thing we want to do is create a custom logger. There are a number of ways you can do this. The most popular way is probably TensorBoard, and that will be hosted locally on your own computer. I wanted something that could be remote, so I'm using weights and biases. So I wrote this custom weights and biases writer that's called whenever logging happens within stable baselines 3. And all it's going to do here is check to see if one of these dictionary keys and values is a scalar type. So it's basically a number. As long as it's not a string, it's going to call weights and biases or wandb.log, and that's going to send it to my project in the current run. And then I can go to my phone, log into weights and biases, and wherever I am, check to see if my agent is actually learning. So now that I have that, I'm going to log into weights and biases. Great, that is logged in. I'm going to create a new weights and biases run. I'm creating a date and timestamp in UTC, and that is my run name. So when I go into weights and biases, I can match it up to whatever's in here. I'm going to create a custom logger using our custom writer. So this is a custom writer. We're going to set it inside of this custom logger. So output formats, here's the writer that we created. Great, now we're actually ready to train. So we're going to try this and let's see what happens. So I'm going to set the initial timeout to like 10 minutes. I imagine if it's too short, like the 5 seconds, it's not going to actually learn anything from the runner just kind of sitting there or just toppling over. We need to let it sit for long periods of time. And when training's like 9 hours, 5-10 minutes isn't a big deal. I'm going to set some initial learning rates. These are just wild guesses based on some of the documentation, the steps per update. That was like 22048, I believe. But I'm going to set it a little lower just because each step takes a little longer. It's not like one step is a millisecond. It's actually like one step is every 300 milliseconds. And so these are just wild guesses for now. And these are hyperparameters that I can come back to. And you notice I'm actually logging them to weights and biases so that I can go to my project in weights and biases and take a look at my notes here. So then we're going to recreate this environment, make sure we have the new hyperparameters like the timeout set. We are going to use the PPO with the CNN policy, and we're going to set the hyperparameters here. And we are going to train and let it go. Hopefully this will work. And I've got it set up for like 20,000, but I'm going to run this a few times and come back and see what our model is doing. I tweaked the model a little bit along with some of the rewards. I also changed the key combo, so instead of letting it try to figure out combos, I reduced that set down to Q, W, and then QP and WO kind of together to see if I could get it to learn to move a little bit more quickly. Ideally learn to stride. We'll see if it actually got there. I then let this train overnight for about 8 hours. So let's see how the model is performing. I'm going to recreate the environment here. And notice I'm not going to set a timeout. Timeout 0 means let it run forever. Don't time out the environment. I'm going to load this model, which should be the best one that I had trained. It's going to be version 7. And then I'm going to let it just play the game. And you notice all that's required here is just that while loop. So it uses the model to make a prediction based on that observation. It takes a step with that action. It definitely tallies the reward. And it just continues until, well, the episode is over. I noticed it immediately got into that squat kneeling position. And it looks like it's attempting to do the scoot, that traditional scoot method forward. But because I gave a penalty to keeping the head below that line, it looks like it's trying to jump up a little bit and get its head above the line. It looks like the environment is stopping at 5 meters, so it gets to its reward. What I need to do here is I'm going to change, I believe I had a threshold. Here we go. The goal marker. We don't want a goal marker anymore. That's saying once it reaches 5 meters, just stop. I was doing that to encourage it to make it to some distance. And we're going to scroll down to where I build the environment and check to make sure that it doesn't terminate early. So here we go. The goal marker needs to be greater than 0, and then we give it that score. And we don't want to terminate if we set the goal marker to 0. Okay, let's try this again. I'm going to go down to where the model is tested. We don't need to retrain that model. We're just changing the environment a little bit. So that goal should be 0, which means no goal in general. We're going to load the model, and let's try playing the game. It goes into the kneeling position, and hopefully it will continue past 5 meters. Let's see what happens. And it looks like our agent made it to that 50-meter mark where there's a hurdle. I don't think the agent's ever seen a hurdle before, and it just collapses on his face. So it looks like we would need a lot more training so that the agent could see that hurdle a few more times and learn how to deal with it. Maybe not jump over it, but just kind of push it along or somehow climb over it. But I'm going to call this good enough for now. I'm going to say that yes, an AI agent can indeed learn to play QWOP. Other machine learning engineers took a crack at this before I did and made much better progress. In 2021, Wesley Liao successfully beat the human record at playing QWOP and wrote this blog post about it. However, his AI-only solution could pretty much only scoot as well as mine did. He had to turn to imitation learning, where the agent mimicked recorded play from himself in order to actually get the character to run. From there, he retrained the agent from play by a top speedrunner and then tweaked the learning algorithm to beat the best time. I think it's cheating a bit, as the AI didn't really learn from scratch, but then again, neither do we. Learning often requires a teacher, and that's exactly what's going on here. I'd like to explore imitation learning some more, but that's going to have to be something for a future episode. In the next episode, I'll choose a simpler game and then show you how to get started with reinforcement learning using stable baselines and gymnasium so that you can start creating your own agents. Stay tuned and happy hacking!